a reminder that for oxidation and reduction occur at the same time. Oxidation is loss of electrons. Reduction is gain of electrons. So the of electrons part is important, and that will become evident to you as we move along. But this is sometimes expressed as oil rig as a means of helping you remember. But the thing is, the loss and the gain is of electrons. You have to remember that bit where even if you remember oil rig, then it's of electrons. And our earliest understanding of oxidation involved reactions that added oxygen to something. For example, that magnesium reaction. Okay, this is oxidation because we're adding oxygen to the magnesium. We now have a broader definition, and that this is it here, that oxidation is loss of electrons and reduction is gain of electrons, and that allows us to explain a whole lot more reactions than simply ones involving oxygen. Now, we looked at some reactions yesterday, and they were all ionic. All those questions on page 7 involved ions. So, for example, this one, where we form ions and so looking at the pathway for the electrons was pretty straightforward. We knew that the electrons were leaving the magnesium metal to form an Mg2 plus ion, and that the electrons were being taken in by the oxygen to form O2 minus ions, oxide ions. Yeah? Well, what we want to look at now is, well, how do we explain what happens in a reaction like this? Because what kind of bonding is present?
Covalent.
Covalent. That's right. And what do we know about covalent bonds? They share electrons. Well, this is where we address the first lie from physical sciences. Not all electrons are shared evenly in covalent bonds. And in fact, what we actually have is a continuum. From ionic to covalent. So yes, we do have purely ionic bonds. Our metals form ions. Cations. But you might have noticed on our periodic tables there's metalloids. We don't talk about them, we just pretend they don't exist. And so metalloids can behave like a metal or bond covalently as well, because they're on that sort of edge, if you like, the edge between metals and non-metals. But even within our non-metals, we can see that sometimes we do have 100% covalent bonding as well. But in the middle here, we have uneven sharing. Okay, and it's this uneven sharing that leads us to have some polar molecules. which we've already seen. Where? Water. Yeah. And so that's a good lead into this reaction here, where we're forming water. The bonds in here, the electrons are not evenly shared between the hydrogens and the oxygen. And so water is a polar molecule. But when we're, from a redox perspective, what we are going to do for our non-metals, or our covalent bonds, is treat them as if they are ionic. And when we talked about water being a polar molecule, which end was positive and which end was slightly negative?
Slightly negative.
Which one?
Oxygen.
Oxygen slightly negative, and we were putting the delta sign, and the hydrogens are slightly positive. Yeah? Because of this uneven sharing. So in our calculation, in our beam counting of electrons, we are going to assume that oxygen has them all in the bond and that hydrogen has lost them all in the bond. Because if we pushed this along further, then that's where they would end up, because oxygen's already got slightly more than its share. Does that make sense? This is why we're choosing to say, oh, well, oxygen's got them all when we're counting. Now, our rule for elements, sorry if I just make myself a little bit more room. So what we have to do is assign oxidation numbers. Or oxidation states. Okay, you'll find these terms used interchangeably. They mean the same thing. For any element, the oxidation state is 0. Okay, because, and this makes sense if we're thinking about it as in terms of forming ions or donating or accepting electrons in the elemental state, then it's all even. Whatever sharing is going on evenly, because they have the same pull on those electrons. So in this reaction, this would have an oxidation state or number of 0, as would this, and this, because they are all elements. And if we look at this top reaction with the magnesium oxide, we already know that magnesium is a group 2 metal and therefore forms a 2+ ion. And so its oxidation state is +2. Now notice that if I write it as the ion, I would write it like that with the 2 first. But if I'm talking about the oxidation state, I put the sign first. That helps to differentiate between the two. Okay, and it's not a superscript like this anymore. It's just a number with a sign. Okay, and the same there for my oxygen, or my oxide ion, is -2. And so if I add these two together, I end up with 0, which makes sense because I started with 0. These need to balance on either side of the arrow. And it wouldn't matter how many I had. It doesn't matter that I've got 2 here, because they're adding up to 0. Okay, but we could multiply this by 2. We could multiply this by 2, but we're still going to end up with them balanced. Does that make sense? Right, so now we are going to apply some rules, and that is here that for oxygen, in this case, can only form the -2, or it can only have an oxidation number of -2. So I'll put that down the bottom here as well. And the hydrogens, in this case, must be +1. But I have 2 of them. And so, if I have 2 lots of the +1 hydrogen, +1 of the -2 for the oxygen, I'll end up balancing them out. I get to 0, and that makes sense because both sides should be 0. Okay? So we've said yes, our oxidation numbers make sense. So if we use these rules, can you tell me which one has been oxidized and which one's been reduced? Because this is a redox reaction. Because something's lost electrons and something's gained electrons. Which one's been oxidized?
Hydrogen.
The hydrogen. So the hydrogen, this is an oxidation reaction for the hydrogen, and obviously then the oxygen has been reduced. I can write these out as half equations. So my oxidation, half equation, I've got hydrogen gas forming hydrogen ions. And this is a gas as well still. And I need 2 electrons to balance the charge. Yeah? My reduction half equation, my oxygen, well, we're forming the oxide ion, still part of the gas here, but to balance this equation, because I've got 2 oxygens on my reactant side, I'm going to need 2 oxide ions. And now if I look at the charge at the moment, so well, my oxidation numbers, my oxidation number over here is 0. This is -2, but I have 2 of them, so I have -4 overall. And these 2 sides need to be balanced. So I need to balance with electrons. I'm going to need 4 electrons on that side because 0 then plus -4 will equal -4. And we've got that -4 on this side. Does that make sense? We're trying to balance out here with electrons, our half equation. But if I wanted to write out a full redox, so the full redox, what do I need to do? We're going to balance with electrons. To balance my oxidation and reduction equations with the electrons. So I need to have the same number on either side of the arrow. So I want to balance out these.
Can you multiply the top one by 2?
Yeah, we're going to multiply the top one by 2. If I write this out with the electrons, then that might help you see what all of the steps. Okay, so by multiplying this top equation by 2, now when I bring the two together, you can see I've got 4 electrons on both sides of my equation. And with my rules of equations, if something is present on both sides, then they cancel out. Okay, so by multiplying the oxidation half equation by 2, so that I now have 4 electrons, means that I have 4 electrons as reactant and product, so they therefore cancel out.
So do you have to write them in?
So you don't write, no. So this is a step that I wouldn't normally do. I'm just putting this step in to show you why we multiplied this top one by 2. And then what we've done is actually just combine them together into the substance that we formed, because I've got 4 hydrogens here and 2 oxygens. Does that make sense? So this is just a way of counting electrons that is important for any element that's a non-metal, but our transition metals as well. Because if we have a look at our table, all of the metals in group 1 can only form +1 ions. That's a rule, and that's what they do. All of the metals in group 2 can only form +2 ions. Aluminium, which is the only metal that we look at in group 13, can only form +3 ions. That's all it can do. And when we get on to electron configurations, this will become clearer to you. But when we look at our transition metals here, they can have multiple oxidation states. And that's why they're transition metals. So these rules are important for these metals and for our non-metals as well, that you're going to need to be looking and seeing, well, what is the oxidation state of that particular substance in question.